Good morning. So today's topic, we will continue on the exponential function, try to finish it out, and start with the LTI system. And what do we mean by LTI system? I started. Okay. So on today's lecture, 26, the reading for today's lecture, page 35 and 40. For next week, Monday, will be the 29th. The reading, same 35 to 40. And there is a MATLAB due date for MATLAB projects. Please refer to Canvas so you can know what's the MATLAB project is. And in Wednesday, the reading between page 40 to 50. And it's also the due date for homework number 3. Also, please refer to Canvas, see what's the homework. Now, let's start today's lecture. So, again, the complex exponential. Signal, as we discussed last lecture. It can be as, for example, f of t or y of t, whatever we can call it, a e power j omega plus theta times t. Then now we have different cases. So first case, when theta equals to omega equals to 0, both theta and omega equals to 0, this yields f of t equals to a, because it will be e power j power 0, which is equal to 1. So we will have only a real number, or sometimes we call it a DC. Because as we know, the DC when the frequency equals to 0, which is the DC special case of AC when omega equal to 0. Then, the second thing, when theta does not equal to 0, but omega equals to 0, this yields f of t equals e power j, or actually e power theta. So it will be as a real number, function of time, but only a real number. Now, case number 3, when theta equals 0, but omega does not equal to 0, this yields f of t equals a e power j omega t, and we can use Euler formula to see as e cosine omega t plus j sine omega t. Then we have case number 4, when both of them are non-zeros. This yields f of t equal to a e power alpha plus j omega theta plus j omega t, which is the same function that we know. So keep in mind, when both of them are zeros, it will be like DC, so only constant. When theta non-zero is function of time, only real parts. So it can be growing or decaying. While when omega non-zero or theta equal to 0, this will be sinusoid. Sinusoidal signal. And we mean by sinusoidal signal is it can be either sine or cosine. So we see we have only sine or cosine. Then, if both of them non-zeros, it's also sinusoid, but with phase shift, which is phase shift theta. Now, let's go and discuss also some special signals, like there's a signal called signal. Have you ever heard of sync signal? Yes. So what do you think sync signal is?
It's like sine over x. It's like
sine x over x.
Yes.
Right. Correct. So, for example, if I assume f of t equal sin of t, basically it will be as sine t over t. Or when I say sink of x, sine x over x. So if we will plot, or also I can, for example, write as sink of pi t equals to sine pi t over pi t. Then the same thing if I say sink of any function or any constant a of t, it will be sine a of t over a t. How to plot this? So the sink function will start here at 1, then it will be like decay. I will do with different color, so. So it is decaying with time. And it is symmetrical. Like this. So here is t, here is sink of t. Or if we want to plot pi, sink pi of t, this should be the same thing. So almost the same thing. But now our concern is the zero crossing. So I mean by zero crossing is this point, this point, this point. How can I know this zero crossing? For the normal case, it will be here as pi, negative pi, negative 2 pi, negative 3 pi, negative 4 pi, and here the last one negative 5 pi. While here is positive pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, etc. So the zero crossings happens when sink of t equals 0. In other words, when sine of t equals 0, and this will be at t equal plus minus n pi. So, and it can be either 0, 1, 2, 3, and so on. That's how we find the zero crossing for the sink. Now, how about if we have sink of pi t equals 0 when we have sine pi t equals 0. Therefore, when pi t equals plus minus n pi, pi's of pi with pi will cancel each other, so it will be plus minus n. Therefore, the zero crossing will be at 0, 1, 2, 3, 4, 5, 6, negative 1, I'm sorry, I miscount. 1, 2, 3, 4, 5, 6, 7, here is negative 1, negative 2, negative 3, negative 4, negative 5. So that's how we determine the zero crossing. And again, this one is sink of pi t. Okay? And the zero crossings, plus minus t, and here plus minus pi and pi. Yes?
Why doesn't it blow up at t equals 0?
Yeah, actually this is a good question. So at t equals 0, it will be like, according to our function, sine of 0 over 0, which is 0 over 0, right? And in this situation, you need to find the limits. You remember, like when we have 0 over 0, you will apply to find the derivative. So the sine will be cosine, which is sine t over t. So when you make the derivative with respect to x, it will be cosine t over the derivative of t will be 1. So it will be cosine t over 1. Then substitute 0, cosine 0 over 1, which will make it 1. That's how we find it. And you will see that this function is decaying with time. It is at the origin, will be max at 1 and will decay. And if you have, for example, sink of t minus, let's say, 2. So in this situation, the sink will be shifted at 2. Then here at 2 it will be 1. Then it will start decaying, something like this. So it's just like where will it start? Okay? Now, a small example here. Express f of t as a sink function, which is I'm gonna plot the waveform, and we need to find how is the sink function looks like. Here's really the big one. This such that use pi is 3 pi over 2. One use negative pi, negative 3 pi over 2. Okay, this function looks weird. So basically, when you look at this question, try, like since there's a major change here, look at this part alone and look at this part alone. So by looking at the right-hand side, I'm going to call it 1, and left-hand side 2. Let's look at number 1. Number 1, it is a small portion of sink of t, right? Sink of t. Because if the crossing at pi, then this is sink of t. So I would say here, number 1, it is like sink of t. But actually, that sink of t is not running the whole time. We're taking only one portion. So it is on at t equals 0, off at t equals 3 pi over 2. Is that right? Then let's look at the second portion. The second portion, it is negative sink of t. So you will see the negative sink of t, it is, you will say like on at 3 pi over 2, off at 0. Right? So this is the most important thing. Now, once you realize this, then now I'm ready to do it as u of t, because we know u of t have to do it on and off. So we will say that number 1, it is sink of t. Since it's on at t equals 0, then it will be u of t minus 0, which is u of t. Then subtract this from u of t minus 3 pi over 2. Now, it will be activated. This is the on time minus off time. That's how what I mean by this. Now, number 2, it is negative sink of t. Then on time, u of t minus 3 pi over 2, and minus minus we make it positive because t minus tau, that's what we used to do. And since tau here is negative 3, so it will be t minus minus 3 pi over 2, which will make it positive. Then subtract it from the off time, which is 0. U of t. Such that again, this is on, and this is off. Okay? Okay, now, how about if I say like, I want to represent this in rate function, other than u of t. We know, recall the rate function t minus, for example, T1 over T0 minus T3, such that T0 is the on time, T3 is the off time, T1 is the sync time. Okay. Now, for number 1, we have the on at t equals 0, which is equal as T0, off at t over 3, which is it will be at 3 pi over 2. Now, in order to find T1, which is the middle, it's going to be T3 minus T0 over 2. So, which is going to be 3 pi over 2 minus 0 divided by 2, then it will be 3 pi over 4. So, I can represent sink of t of u of t minus u of t minus 3 pi over 2 as follows, which is sink of t rect of t3, or which is t minus t0, t minus that of from t1, which is 3 pi over 4 divided by t1 minus t2, or t3 minus t0, which is going to be as, actually I missed that, t3 minus t0, just make sure, fix this, t3 minus t0, then t3 here, which is the off time, 3 pi over 2, minus 0, which is 3 pi over 2. That's how we represent this in vectors. That was for the number 1. Number 2, on at negative 3 pi over 2, off at 0. So it will be T1 will off minus 1 over 2, which is going to be 0 minus negative 3 pi will make it positive pi over 2, which is 3 pi over 4. Then the width, or actually when we do the rects, it will be as negative sink of t. Here it was u of t plus 3 pi over 2 minus u of t, which will make it as sink of t times rect of t plus 3 pi over 4 divided by t, or which is the width here, 0 minus 3 pi over 2, which is going to be minus negative positive 3 pi over 2, so it will be 3 pi over 2. And remember, those are multiplied. So I would say as sink sink. But keep in mind here, I think the thing that I missed out, which is this should be a negative sign. Should be a negative sign, because here on minus off. Just look at the words. Sponge, that's it. So that's how we do it in terms of rates. Then the overall function is 1 plus 2. Just keep in mind to add 1 plus 2 to get the overall function. Either it's sync representation or rect representation. Okay? Now, let's go to another function. It's called signum. or sine signal. So, have you ever heard of it? Signal or sine signal? Oh, that's why we're here. We're learning new stuff. Then, signal, or we put signal, or sometimes we put it as sine signal. We used to say f of t equal to, we shortcut SGN, that's the shortcut, and even you can find it in the MATLAB or the different signal like SIGIN, SGN, signal function, equals to 1 when t larger than 0 or -1 when t less than 0. It's very similar to the unit step, but unit steps start from 0 to be 1. But here, it will jump from -1 to 1. So, the plotting of it will be like this. Here's 1, here's 1. And that's signal ft. And the same if you apply phase shifts, like if you say signal t minus t0, then it will be like, here's t0, then it will go like this. Okay? So again, this is very similar to u of t, but the thing which is it's activated, sometimes negative, it will jump from negative to positive. It looks like you're driving, like going wrong other direction, then at t equals 0 you switch your direction. Because the negative sign means 180 phase shift. This means in vectors as goes to opposite direction. So how can we represent the sine function in u of t? It will be as u of t minus u of negative t. That's how it looks like. Or we can say it is 2 u of t minus 1. How to validate this? U of t like this. U of negative t, it is u of negative t, it is like this. Then when you do the subtraction, the net result will be like this way. Or whenever you say like u of 2t is 1, here's 1, here's 1, u 2 of t, 2u of t, here's the magnetic 2, 1 is here. Then when you do the subtraction, when you subtract the first part, 2 minus 1 will be 1, 0 minus 1 will be 1. Okay? So that's how we derive the function, or typically that's the signal function. Any question? Let's move to chapter 2, which is linear time invariant systems. Linear time invariant system. So as a shortcut, we will say LTI. Linear time invariant. Okay? Now, let's talk a little bit about what does linear mean. Linear system can be achieved if scaling and additive properties satisfied. Now, what does scaling, what does additive? Let's discuss. Let me go first for scaling. So scaling If, for example, I have x of t and it's entering the system, so you will have y of t. But if I entered cx of t, it will give me z of t. Now, if z of t equals to cx of t, or actually cy of t, then it is scalable, such that c is not function of time. What does this mean? Let's assume we have the following function with this signal. What do I mean by scaling? If I have this signal, scaling means keep the same property, but maybe with larger magnitude, something like that. That's one example of scaling. So if it's applied like this, then that's fine. We can know it's scaling. So how to apply the procedure? Is it scalable or not for some functions? So the procedure to check scalable function, you can replace x of t by cx of t. Replace y of t by cy of t. Then can you make it as cx of t equals cy of t? If yes, then scalable. Okay. Replace cx of t, y of cy of t. Then yes. Okay. I think it can be fine. Let's see some examples. Example number 1. You have y of t equals 3x of t. Now replace every y, cy of t, every x, 3 cx of t. Now can we make it as c y of t equals c 3x of t? Yes, we can. Then it is scalable. Another example. You have y of t equals 3x of t minus 5. Let's replace every y of t by cy of t, every x of t by cx of t. Can we take c as a common factor? In the right hand side, left hand side, yes. In the right hand side, we can do it for only x of t, but we can't do it for the 5, right? So it's not scalable. That's an example. Okay? Does this make sense? Now, another thing for checking scalable or not, which is if we have the following system as a differential equation. d by dt y of t plus 6 y of t equals 4x of t. Now, in this situation, again, we will replace every x by cx, every y by cy. So it will be d by dt c y of t plus 6 c y of t equals 4 cx of t. Can you isolate c in each side? Yes, we can. d by dt y of t plus 6 y of t equals to c 4x of t. Then, yes, it is scalable. Number 4, another differential equation. X of t, d by dt, y of t, plus 6 y of t equals to 4x of t minus 5. It is y of t. Let's check, replace every x by x of t, every y by y of t. So it will be d by dt c y of t plus 6c y of t equals 4c x of t minus 5. Now let's isolate c. C d by dt y of t plus 6 y of t. For this side is fine, or for the other side there is a problem. C 4x of t, we have negative 5. So negative 5 creates a problem, so it's not non-scalable. Okay? Now the other thing, additive property. Additive property says that if you have a system with x1 of t, it will give you y1 of t. If you have the same system with x2 of t, it will give you y2 of t. How about if you enter these two inputs together? If you enter x1 plus x2 for the same system, will it give you y1 plus y2? If yes, it is additive. So this we'll call it as z. So if z of t equal y1 plus y2, then additive. If not, then it is not additive. Okay? So let's see example about it. Make sure if we understand this word. Example. We have here is x of t, d by dt, y of t plus 6 y of t equals 4x of t. Here, y of t. Now, we need to make sure, is it additive or not? So what I'm going to do is, let's try to make x1 or y1. So let's make d by dt, replace every y by y1, every x by x1. So dy1 of t plus 6y1 of t equals 4x1 of t. Now how about y2? d by dt y2 of t equals 6y2 of t equals 4x2 of t. Now let's do their sum. Sum of them together. So when we sum of them, it will be as d by dt of y of t plus y2 of t plus 6 y1 of t plus y2 of t equals 4x1 of t plus x2 of t. For x1 of t plus x2. Okay. Now, is this the same? This is the first thing, which is this is number, I will say this is number 1. Number 2, for the same function, replace every 1 of t by y1 plus y2. So which will make it d by dt. Every y of t will be y1 plus y2 plus 6 y1 plus y2 equal 4. Replace every x by x1 plus x2, x1 plus x2. Now, since 1 and 2 are equal to each other, then it is additive. Again, what I did here, so first thing, replace every y by y1, every x by x1. Then replace every x by x2, every y by y2. That's what we did here and here. Then do their sum. After doing their sum, group them together. We will get equation 1. The next step, go to the set equation, but instead of replacing y1 and y2, replace y1 plus y2 and replace x by x1 plus x2. Then, if these two are the same, then that's perfect. This is additive. Now, in order to get a linear function, the system must be both additive and scalable. So how can we make this test, or to make sure is this system linear or not? And instead of doing these two tests, so I have a better approach, which is to check linear system, linear or non-linear systems. We will check them together. So basically, we will check this things, which is make sure if ax1 plus bx2 will yield to ay1 plus by2. If yes, then it is linear. If no, it is not linear. Okay? So basically, what you are going to do, the procedure, so replace, in order to check is it linear or not, x by ax1 plus bx2. Then get your equation. We'll find the results. That's the first step, number 8. Or step, I won't say like step number 1. Step number 2, replace or find y1 equal x1 of t. Then find y2, relationship y2 yields to x2 of t with x2 of t. After that, make an ay1 plus by2, find the equation. So this will be equation number 2. Then if equation 1 equal to 2, then it is linear. If not, then it is not linear. That's the procedure for the first property, which is that I'm going to call it linear or non-linear. Now, before going to examples, I would like to give you a couple of properties, also as a definition. Then we will apply all of these 3 properties into examples, common examples. So let's go to another definition by called stable and unstable system. Most likely here, we will look for bounded inputs, bounded output stability. If I have bounded inputs, will it give me bounded outputs? And this thing we call it BI as bounded inputs, BO as bounded output stability, BO stability. So we need to make sure that it will give me a stable system. Maybe you will hear about stability also later in the control system course. But here also we will use it. Most likely we mean by bounded something limited. It will not equal to either plus or minus infinity. So basically, we want to make sure when you make, especially like we use it a lot in the control system, if I apply my controller, will it give me a stable result, or will it will make, for example, the motor run faster, until burned or turned off? Or like when I make the temperature, will make the temperature to reach a certain limits, or will it stay heating until like broken something? So make sure everything is safe. So everyone's looking for stability. Sometimes stable system does not mean the system is working in my target, like what I want to be, but it means it is working without problems. But it does not mean I'm doing control. So most likely, in our analysis, we are looking for a stable system. How can I check if this system is stable? So we have x of t, and here's my system, and here's y of t. So what I'm going to do, I'm going to replace every x of t by a symbol or a constant m. I'm going to replace y by r. So if m is limited, is non-infinity, and all of them, these two numbers are real numbers, of course, constants and real numbers. If m is limited, will it give r as limited, or plus or minus infinity? If it is r will be limited, then it will be still. If it will go to the infinity or something, infinity, or we'll say like or undefined, then it will be unstable. Okay? That's what we mean by stable or unstable. Make sure if we give good input, will give good output. As an example, when you drive a car, if you press fuel, it will race or it will accelerate. Press brake, it will deaccelerate, right? This is stable system, right? Well, imagine that, what's an example? Like if you are driving a car but you didn't have access to the brake, then it will keep accelerating, right? You cannot control it. So keep accelerating, no matter what you are giving, you are doing. If you cannot make, for example, the brake, then it will be deaccelerating, which will make it unstable. Now, the third property, invertible or non-invertible. So basically, when I have a system, x of t gave me y of t, can I figure out a way to modify that or just change the equations? Can I make y of t with system u, I can call it system 2, to give x of t? Then yes, then invertible. No, non-invertible. One example, like when you cook food, you cannot get it back to the origin, right? There's no way. But when, for example, you are driving a car with no speed still, then driving, then you can at any time to go back to the original situation. So, I mean, you can reverse the situation. But some other parts which is non-revertible, which is no way to modify, to go back to the origin. Okay? So we have three properties that we discussed now, which is linear, then stability or linearity, stability, then invertible. Here's C, A, which is invertible. Let's do this check for the following examples. Let's start with number 1. When I have y of t equals to 3x of t minus 5. Let's check number A, which is it linear or not linear? So in order to check this, according to our procedure, the first step, replace every x by ax1 plus bx2. So this will yield the equation to be as 3 ax1 plus bx2 minus 5. Okay? So I'm going to call it as equation A or equation I. Now, part B, or actually still in stability. So this is the first thing. The second thing, replace or find y1, which is 3x1 minus 5. y2, 3x2 minus 5. Now ay1 plus by2, this yields to 3 or a times 3x1 minus 5 plus b times 3x2 minus 5. As a result, this will yield to 3 ax1 minus a5 plus b 3x2 minus 3, 5. Let's try to group a and b together. I'm sorry, group a and x. So it will be as 3 ax1 minus bx2 minus a times 5. Now this is equation number 2. Does equation 1 and 2 equal to each other? No, because the 5 here is problem. Therefore it is non-linear. Because 1 does not equal to 2. The next check is it's stable or unstable. So again, we have y equal to 3x minus 5. Let's replace y by r, x by m. So y, r equal 3m minus 5. Now, the question is, if m is bounded or is limited, is there a way to get y infinity? No way, right? Assume m any number but only real number, and also assume it like just a constant. So will it go to the infinity? No way. So therefore, it will be only constant, so it will be bounded. So therefore r is bounded or limited, and it will be stable. Or something we call it bounded inward, bound outward stable. That's 6. C, let's assume to find the inputs, which is, or to y equal 3x minus 5, we need to make invertible. Can I get x? So x will be y plus 5 over 3. And it's valid anytime, right? There is no way to get an undefined function. So we will say it's invertible. So this system is invertible, stable, but the situation or the thing that I have, it is nonlinear. Nonlinear because the existence of negative 5. Let's do another thing, which is y of t equal x of negative. Now, to check the linearity, let's make it fast, which is, we will say that x1, ax1 of negative t plus bx1 of negative t. That's the first thing, which is equation 1. The second thing, y1 will lead us to x1 of t, negative t. y2 leads to x2 of negative t. So ay1 plus by2, this yields to ax1 negative t plus bx2 negative t. Then, since 1 equals to 2, therefore it is linear. The second thing to check is its y equal x negative t, because it's stable or not. So basically here r equal to m, then of course it is stable. Because when m is bounded, m will not be infinity, of course r will not be infinity. So it's bounded, inward, bounded, outward, stable. Now the last thing, to get x of t, y equal x of negative t, therefore x of negative t equal to y, then of course it is invertible. Okay? Now, number 3, y of t equal cosine of x of t. Now, how can we check, is it linear or non-linear, invertible or not? Okay, so let me write some questions, so we will do this next lecture. But I'm going to write this question, so this for you, the tests, these three properties. We will have your time, for x of t, and number 6, y of t equal x of t, changes within this language. So these additional four examples we will do in this lecture. So see you on Monday. Have a good day.